Electricity in almost every car is 12 volts. Most trucks and lorries use 24 volt systems and older cars used 6 volts. Fuses in a car and at home are rated in amps, and if you put a big amplifier in your car, then you'll find that it's rated in watts. These numbers are all measurements of the movement and the use of electricity. And in this video, I'll explain volts, amps and watts. And these are units that you'll come across every day working on cars. And we'll explain them in nice, simple terms. Electricity moves around. And in 1747, Benjamin Franklin spent a lot of time thinking about why. In the end, he reasoned that electricity was a little like bookkeeping, where objects had a certain balance in their electrical accounts, and just as an account could be in credit or debit, so an object's electrical balance or charge could be positive or negative. He thought that electricity flowed from positive to negative, and the world accepted this flow and has worked on it ever since. Much later, when scientists got down to the level of atoms, it turned out that electrical flow was actually caused by a movement of pieces of atoms called electrons, which moved from negative to positive. It's the opposite direction than what Franklin discovered. But it doesn't matter, and we work on the basis of electricity flowing from positive to negative, what's called the conventional flow. It's only when you get down to electrochemistry that you need to worry about the movement of electrons. And in cars, this means that we always think of electricity being supplied by the positive terminal of the battery and returned to the negative. If we use a conductor to connect a point with a positive charge to a point with a negative charge, then electricity will flow between them in an effort to balance things out. And the bigger the difference between these 2 points, the greater potential there is for electricity to flow. The difference in charge between 2 points in a circuit is called the potential difference, although in the shop, in the garage, in real life, we always call this voltage. Now, potential difference, or voltage, is measured in volts. And difference is the key word here. When we measure voltage, we're not looking at a single place, but 2 places and the difference in charge between them. The easiest way to visualize voltage is as a difference between 2 tanks of water. Let's say we have 2 tanks of water next to each other. Tank A is full and tank B is also full, and we connect a pipe between them with a tap on it. When we open the tap, nothing happens. The difference between the 2 tanks is 0. If we empty half the water out of both tanks, then what happens? Again, the difference is still 0, so nothing happens. But if one tank is half empty and the other is full, then we have a difference. And when we open the tap, water will flow between them until they're at equal levels. There is a potential difference, and that difference will cause water to flow. And the bigger the difference, the stronger the flow of water is going to be. If I showed you just one of those tanks and I asked you to tell me the potential difference, you couldn't do it because you don't know whether the other tank has more or less water. And that's why a voltage is always taken between 2 points, because it's the difference between them. We measure voltage using a voltmeter, and it's the most common electrical measurement that you would make on a vehicle. Now, long ago, a voltmeter was an independent machine of its own, but these days, everyone uses an electrical tool called a multimeter, which works as a voltmeter and has loads of other functions as well. When I measure, put this down here, we're on volts mode. When I measure the voltage between the positive and the negative terminal on this battery, we're going to get about 12.5 volts, something around there. 12.73 volts we have. Now, if I take both my probes and I put them on the negative terminal, I now see a voltage of 0. And both probes on the positive terminal, I also see 0. And the reason is that there's no difference in charge between the 2 probes. It's only when we're across 2 differently charged points that we see a voltage. Voltage is the pushing force driving current around the circuit. In a car, we're normally dealing with a voltage that we nominally call 12 volts, but it can actually be anything between 12 volts and 14 or 15 volts, depending on the charging system. Now, you'll measure voltage all the time on cars to see how much voltage is getting to a component or what voltage is coming out of a sensor. So that is voltage, a force pushing electricity around. Sometimes you'll hear it called electromotive force or EMF. Potential difference, voltage, is all the same thing. Now, current is the rate of flow of electricity. Just like the water flowing along a pipe in our water analogy, current is measured in amps. And to measure it, we only need to look at a single point on a wire to see the amount of electricity flowing along it. Now, those water tanks that we talked about, well, they're not just ordinary tanks. They're actually some imaginary fish storage tanks. And the tanks are filled with lots of little fat fish. The fish are flowing from one tank to another. And to know the flow or currents, we can count the number of fish flowing along the pipe. But with electricity, instead of fish per second, we're interested in the flow of electrons. And we measure this flow in a unit called the amp. There are two ways we can measure the flow of fish. We could split the pipe and connect it through some sort of fish counting machine. The machine counts the fish flowing through it, and this is one way of measuring electrical current. Instead of a fish counter, we use a device called an ammeter, and just like a voltmeter, it's a function on our multimeter. Now, to measure current, we run the electricity through the ammeter and it tells us the current passing through in amps. But I said there's another way of measuring the flow of fish. I mean, we could just use a transparent pipe and count the fish going past. Is there a way that we could see inside a wire and measure the current? Yes! Remember Ørsted and his compass back in 1820? He put the compass next to the wire and found that electrical current flowing through a wire creates a magnetic field. We can measure the magnetic field being created by a wire and it will tell us the amount of current flowing. To do this, we use a current clamp. It clips around a wire and measures the strength of the magnetic field, converting that into a figure for amps. Now, these are very, very common in the automotive sector. You'll find specialist automotive multimeters that include a current clamp like this one. If I want to measure current on a vehicle, I'm always going to reach for a current clamp first. Why? Because firstly, I don't want to have to break apart circuits to insert an ammeter. It's much quicker and it's much cleaner to use a clamp. And secondly, there are places on a car where big currents are flowing, much bigger than we could possibly put through this. Look how thick, wait a minute, where's the starter motor cable? Look how thick the starter motor wire is. We're talking hundreds of amps flowing through here. And if I run those hundreds of amps into this delicate thin wire and into this expensive delicate multimeter, then we'll have an expensive puddle of yellow plastic on the table here. Since a clamp meter is looking from the outside at the magnetic field it's just observing, it can measure much higher currents. Before we leave behind my slightly contrived fish tanks analogy, we've got another thing that affects the flow of fish. There are things that we can do with the pipe that will either increase or reduce our fish current. A thinner pipe will give a lower flow. A thicker pipe and we've got a higher flow of fish. If we put a water wheel in the pipe and used it to turn a little fan, then the flow is reduced. And if we put a bigger fan on the water wheel, then we're doing more work and the flow is reduced even more. This is the same as the concept of resistance in electricity. Electrical resistance is a measure of how a material or a device reduces the electrical flow through it. We measure electrical resistance in ohms, and it's measured with an ohm meter, which is, of course, part of a multimeter. And you can measure the resistance in something by probing either side of it with a multimeter in resistance mode. Let's probe some things. We're in resistance mode. The resistance of conductors is low, 0.2, 0.1, very, very low resistance. The resistance of insulators, like this plastic, is so high that we don't get a reading. It's a massively high resistance. If we choose something like a pencil lead, which maybe I have, here's a pencil, or it has a rubber on the end so we can't get to the lead. That's that problem solved. Right, let's measure the resistance of this pencil lead. Probably this is made out of dust or something, I don't know. Maybe they don't make them out of conductive material like graphite or lead anymore, but let's see. What do we get? Aha! We have a reading. There we are, interesting. So, the resistance of lead, which is somewhat of a resistor, is about 1.6 kilo ohms, 1,600 ohms. So, you can measure the resistance of things, and you measure the resistance across the thing that you're measuring. The multimeter measures resistance by putting a voltage across the probes and measuring the amount of current that flows. Now, along with voltage, resistance is the other measurement that you'll make all the time in vehicles. Many sensors act as variable resistors, where the resistance depends on the thing that they're measuring. You'll often find the resistance of a component in the manual, and testing this resistance is going to tell you whether the sensor is working or not. Now, this is the coolant temperature sensor, and it tells the engine management system the temperature of coolant flowing around the system. We can find specs for the sensor based on its part number or the vehicle's make and model, and those specs will tell us the expected resistance. For us, at different temperatures, we have a table of resistances. And in here, it's about 15 degrees. So looking at this table, we're expecting to see a resistance of around 4,300 ohms or so. Let's test our coolant sensor. What we need to do, pop our multimeter on resistance mode, and then we just probe across the two terminals, which will output a voltage if this was on the car. And we're going to find a resistance. And here we go. With 2.9 kilo ohms. That's quite a bit lower than what I expected, but it's relatively within spec. Now, what we would do if we suspected a fault with this coolant sensor, I have no idea if this works or not, but I suspect it's fine. If we really suspected a fault with this, we might throw it into some hot water and check its output, its resistance, at various different temperatures of water and compare them with the specs here. Resistance is the thing that ties voltage and current together. If you were a fish tank storage expert, you'd be able to look at the difference in water level between two tanks and the size of the pipe, and you'd know what the flow rate of fish would be. Or you could look at the size of the pipe and the flow rate of the fish, and you'd know the pressure difference between the tanks, which drives that number of fish through the pipe. And it's exactly the same with electricity. There's a clear relationship between voltage, current, and resistance. And given a voltage pushing and the resistance against it, you can calculate the current flow that will result. And the formula for this is voltage equals current times resistance. V and R are for resistance and voltage. I is what we use to stand for current. Now, another way to write this, and the way that I like, which is the easiest way to work out each individual thing, is to write this in a triangle. So we have V, I, R. And then, if we need to calculate resistance, we cover resistance, and we have the formula voltage over current, V over I, voltage divided by current. That gives us the way to calculate each of these parts. Say we're looking for voltage, we cover the V, it's I times R. We're looking for current, it's voltage divided by resistance. So these triangles are always an easy way to remember simple formulas. It's not so important that you remember this formula, but it is important that you know that voltage, current, and resistance are related. Now, anything that you've seen rated in watts, kilowatts, or horsepower is referring to power. And power is the rate of doing work. And it's not a concept limited to electricity. It can be applied to any system or machine. The power output of an electric motor can be compared to the power of an internal combustion engine, or to a light bulb, or detonating 100 tons of TNT. Power is measured in one of two units. The old school horsepower, which is based on a comparison with the output of a horse, or if you prefer your measurements to be a little more sane, the watt. And the Watt, confusingly, is named after James Watt, who developed the steam engine and came up with the concept of horsepower. Now, since watts and horsepower are measuring the same thing, power, you can convert between them. A horsepower is about 750 watts. We'll talk more about horsepower when we discuss engine power because it's much more commonly used there than in electrical circuits. And I guess that's because it makes more sense to compare engines with horses than to compare light bulbs with horses. Now, in electrical systems, power is the rate of current flowing multiplied by the voltage pushing that current. Written down, that's P equals VI. Again, the P for power, V for voltage, and I for current. And you can write it down in a little triangle. P, VI. You cover the thing you need to know with your finger, and it gives you the formula. So if we want to know voltage, and we have power and current, we know that power divided by current gives us voltage. Because often you'll have numbers for current and voltage but not power, or you'll find a label with power and you need to calculate the current that a component's going to draw. Let's look at our starter motor, for example, and the label here shows that this draws a current of 400 amps. So that's our current. We already know the voltage is 12 volts. So using our triangle, we can calculate that power is voltage times current. That's 12 times 400 amps gives us 4,800 watts or 4.8 kilowatts. Now, if we look at this headlight bulb, we find its power is printed on there, which is 55 watts. And how much current does it draw? Well, again, to the triangle. We cover over current, we find its power divided by voltage. So we have a power of 55 watts divided by 12 volts gives us around 4.6 amps. And that is the current drawn by our light bulb. Okay. What we've covered here is enough to understand all the car's electrical systems. Let's just quickly revisit those concepts. Voltage is the force pushing electrons around a circuit, a bit like pressure. Current is the rate of flow around a circuit, and resistance is, well, the resistance to that flow. And we've seen that these three are related by a simple formula. Voltage is current times resistance, V equals IR. And power is the ability of a system to do work. High voltages or high currents or both get lots of work done. And electrical power is measured in watts, and the formula for it is power equals voltage times current, or P equals VI. The end.